And hello everybody, and it's session 3 of the AS revision sessions. Steve Jones is going to talk about lasers, and my name is Jane Owen.
Hello everybody. Before we start on lasers, there's a few things we need to understand before we actually look at a laser itself. And these are some key ideas from 2.7. So there's a couple of items from 2.7 and we'll actually move on to lasers themselves. So to start off with them, before we understand lasers, we need to understand something called a continuous emission spectra. Now, a continuous emission spectra is things like white light from a filament lamp, as we've got here, pass through a prism or diffraction grating, and what we see is, for want of a better word, a rainbow. In physics, we call that a continuous spectrum. So all the wavelengths of visible light from red through to violet are present. So all wavelengths are present, and that's the key. So it's a continuous spectrum. And white light, filament lamp, anything like that, prism, we have the spectrum of colors. Now, line emission spectra is slightly different. So you can get line emission spectra from things like hydrogen, neon. You can actually get it from your lamps, your mercury lamps on the ceilings of your classrooms. But essentially, how it's formed is you take a hot gas, and when we say hot gas, we mean hotter than its surroundings. Right? Pass it through a prism, and what you have is these lines. Right? So these are specific lines at specific wavelengths. Right? So they are at specific wavelengths. And put together, if you're looking at your fluorescent tube in your classroom, together they produce white light. But if we put them through a prism or diffraction grating, we can actually see very distinct lines. And this one happens to be, if I remember correctly, hydrogen. But don't quote me on that one. All right, but again, caused by hotter gas than the surroundings through a prism, and we get these line emission spectra. Now, in between these line emission spectra, we have dark areas, right? They're not black. It's important to know they're not black because it is light in there. However, it's too faint for our eyes to pick up. All right, so we have these bright spectra on a dark background. So that is emission spectra, and I'll show you how that's caused in a second. I'll explain how that's caused in a second. The third one is absorption spectra. Now, if you look, it's the same element, right? So I think it's hydrogen, although I'm not going to quote myself on it. And where the bright lines are in the emission spectra, you've got dark bands in the absorption spectra. So we've got the same gas here as we have up here, whether it be neon, whether it be mercury, whatever it is, hydrogen. And this time we pass white light through it, and these wavelengths absorbed by that gas, and the remainder of the light goes through the diffraction grating or prism, and that's why these appear to be missing. So again, these are dark bands. They're not black. And there's a reason for that, because as these photons of light of that specific wavelength are absorbed, they're immediately emitted back out again, but not in the direction of the prism, and therefore not in the direction of our eye. They could be emitted in any other direction. So while they're dark, they're not black. So there is light in there, but it's not as intense as the surrounding light. So we've got three. We've got continuous spectrum, line emission spectra, and absorption spectra. So how are these formed is, I think, key to where we want to go with this. There's my mouse gone. There it is. All right. So let's take a very simple model of an atom. So we've got the nucleus in here, and in here we've got all the atoms, where the nucleons, right? I'm just not worried about that. And outside we've got these shells, as we call them, right? In chemistry, physicists call them waves potential. It doesn't matter. So you've got these shells which electrons apparently live in. All right, there we go. Now, if the electrons always like to be in the lowest energy level, so as you may well know, there's 2 in that one there. Now, if we were to excite this electron, it moves up. Now, the energy is required to move up. You may know it's E equals hf. If you didn't know that, you do now. All right, it has to be specific. So it's a specific wavelength, or in this case, frequency of light, that will get it to go from this energy level or this state into this state. And by doing so in this direction, or if it's going up, it absorbs a photon. Okay. So in this case, if this was part of a gas, this would produce a dark line. Now, similarly, if you had one excited for some reason and it falls down, right? So it falls down to there, it's going to give off exactly the same frequency of light, because that's the energy gap between these two energy levels, right? So it's going to give off exactly the same frequency or wavelength, but this time it's going to emit a photon of light. And that's how emission spectra is formed. So it's a very specific wavelength which is emitted, and therefore we see either that for emission, all right, if the electron is falling down from a higher energy level to a lower one, and that for absorption if it's moving from a lower energy level to a higher one. Also, it doesn't mean to say it's going to go from where's my pen? There it is. From here to here. It could go from here to the next energy level out here. So we could have an energy level out here, and it could go directly to there. What we can do with this is we can create something called a potential well. And this is a potential well. Here is an emission spectra on a potential well. So they're all emitting. I'll explain that in a second. So if you notice, this again is for hydrogen. And we've got down here that n equals 1, this energy level, if you like. All right, so this could be that this is the ground state. All right, that's the lowest level that any electron would like to be in. And if it's full, it fills up the next one. So that we'll call this E equals 1, just for simplicity. All right, etc. I'm not going to go all the way up. All right, you could say that is E equals 1. I'm just stating that that's what I'm calling these for now. All right, or n equals 1, n equals 2. Right, doesn't matter. That's electron shell, if you like, 1, 2, 3. All right, now what we've got here is the key thing is here. If the electron is down here, it's got an energy of minus 2.18 times 10 to the minus 18, which means it needs 2.18 times 10 to the minus 18 to actually leave the atom, to be liberated from a surface or to be a free electron, right? So it's negative. Think of it as you walk in along a footpath. Potential energy wise, you've obviously got 0 because you're walking on a footpath, but all of a sudden you fall down a manhole cover and end up at the bottom of the manhole cover. What you need is energy to get out of there. It doesn't mean to say you've got negative energy, it just means you need energy to get back to 0 potential, because you've defined 0 potential as where the footpath is. So that's what this is sort of about. That's why it's negative. It's because it's fallen into this potential well, it needs that much energy to get back out again, and that's fine. Now, within that, you've got these energy levels, or these electron levels, doesn't matter how you call it. And each one, to get from one to the other, you need a specific amount of energy. So to get from n equals 1 to n equals 2, I need the difference between 2.18 and 0.54. So that, if I have that, E equals HF, all right, so I have the right frequency, that's exactly that. I will jump from there to there. Similarly, if I'm here already and I drop back down, I'll emit a photon. In this case, it's going to be a UV photon, exactly the same as what would be absorbed if UV photons were incident on myself as a little electron. And then we can see here, depending on the energy level drop, depending on the wavelength of light, because each drop is a different energy, right? So here, the energy between this one and this one is greater, so E equals HF, we've got green light. That's red light, so that's the least energetic, and then we go all the way to 411 nanometers, which is violet, ultraviolet area, and 434 is about blue. So, and that is a potential well. All right. So just to recap, it's negative because you need the energy to become a free electron. Every time you move up, you're absorbing that fixed amount of energy. Doesn't matter where you're going from there to there, or from there all the way up to there. Right, you will need that difference in energy between there and there to move up. And if you fall back down, you're releasing exactly the same amount of energy. And hence, we look at our spectrums up here, they're in exactly the same place. Right, so that wavelength there, or that frequency there, is exactly the same as that frequency there. just one is moving down, it's emitting light, and one is moving up the energy level and absorbing that energy that that light is producing, that photon is producing. So that is the bit that you need to know before we can go on to lasers. All right. So let's go on to lasers themselves then. Right. So there are three types of emission. So I've talked about emission, right? So we talked about emission spectra, i.e. this one here falling down from one energy level to the next one, giving off a photon of light. So we've got this two types, of emission spectra and one type of absorption. So excitation is when we absorb a photon. So if I was to draw that, right, let's have a look. Let's draw that. We'll call that excited state. Doesn't matter which excited state it is, right? Whether you're going from n equals 1 or n equals 2 to n equals 3 or n equals 4, doesn't matter. All right, and we're going to call that the ground state. All right. So when a photon comes in, right, here it comes, there it is, and it has this energy E equals hf, right? If it's exactly the energy difference between there and there, it will be absorbed, and the electron will move from there to there. And once it's there, we say it's now excited, right? And it will stay there for a fraction of a fraction of a fraction of a second, right? And then what it does, it doesn't like to be there because every electron wants to be in the lowest possible energy state, and this one isn't in the lowest possible energy state. It can go lower. There's, we're assuming that there's no electrons down here, therefore it will drop back down. So if we're in the excited state, so let me just quickly doodle that. So again, we're in the excited state, and this is the ground state. What happens is immediately after, and we're talking, nanoseconds, right? It will drop back down to there, and because that energy level is equal to E equals hf, exactly the same as what we've got here, it will emit a photon. Now this photon is in a random direction. Let's just have that. It's in a, where am I writing? There you go. A random direction and phase. So we don't know where that's going to be, right? We knew which way it was, where it was coming in, right? We knew the angle or the direction it was coming in, but when it's been absorbed, it can come out in any direction. I've just shown it continuing on, but it may not be. It may have zoomed up here somewhere. It may have gone this way, or it may have gone that way. Who knows where it's gone? So it's a random direction. All right. Now, what we don't want for lasers is this random direction. We actually want it to go and do what we want it to do. All right. So what we do, we have something called stimulated emission. And to do that, what we do, let me just doodle my ground state again. And this is the fundamentals for lasers. And this is really the exciting part of it, if you like. Right, so if we have an electron that's already excited, and we can keep it there, right? We've said it's a nanosecond. We can just keep it there long enough for another photon to come in of exactly the right energy. Again, E equals hf, right? Between there and there, right? Same amount of energy as this one has absorbed previously, all right? And it comes in. What it will do is it will stimulate this one to fall. I guess it's a bit like walking past a shelf of bottles on, and that electromagnetic part of that photon wobbles it and it falls off the shelf, right? In this case, it's going to fall down from the excited state and it will drop. So as this photon excites it or wobbles it, right, the EM part of that interacts with this, it'll fall down. This photon hasn't been absorbed, so it will continue. There we go, there it is. But this photon now will, or this electron will give off a photon of light. Again, E equals hf. But because it's been stimulated, it will go out or leave, or it will be emitted in exactly the same direction. So what we have here is the same phase and direction. And we call that, as you probably already know, coherence. So what we have is now is coherent light. They have the same phase, they have the same direction, they're the same frequency. All right, so everything about these two is identical. And that's what we're looking for with lasers all the time. So let's go back to what laser stands for then. Laser stands for light amplification by stimulated emission of radiation. How to think then. All right, so light amplification by stimulated emission of radiation. So this stimulated bit is where the acronym laser comes from. So that's what we're trying to achieve. So that's what we need to do at all times. Now, this all depends about having this electron or many electrons up here. So the thing that we need to know then is something about population inversion. All right. So to get lasers, we need to understand the next terminology, population inversion. Well, it says here in your specification that this idea that N2 equals or is greater than N1. What we mean by that? Very, very simple. Let's take our electron or our potential well. All right. So what we got was, let's do a couple of let's do another one in there. Let's do a couple of energy levels here. I've got to try and repeat this again in a second. So normally, right, so these are my energy levels. That would be perhaps E equals 1, whatever I want to define it as, equals 2, etc., etc. Normally, they're all in the ground state, right? They're all sitting down here. And you may have an excited one up there, right? But what we've got is the numbers up here, all right? So N2 is much less than N1, i.e., right? Or E2 is much less than E1. Right, so all these numbers or all these electrons are down here. There's more of them here than there is up here, which is not great. So for a population inversion, we need to have the opposite. So let me just repeat what I've done over there. There we go. All right. What we want is more of them up here. Doesn't matter where they are. What have we got? I've got 5. So I want, more of them up there than down here. So that's a population inversion. I know I've only got 2 in there, and I've got 1 in there and 1 in there, but I've got them all excited. So here I've got N2 is greater than N1. And that's a population inversion. They're not where I want them, but that's the definition of a population inversion. Is the idea that they're more in the excited states than there are in the ground states. And that's what we're looking for. Because if we can get them in the excited state, we can get this stimulated emission. If they're all in the ground state, we can't have stimulated emission. Okay, we can't, because there's nothing to stimulate. But if we can get them up there, we can stimulate them to fall down using the right light or the right photons coming in, and they will fall down, giving us coherent light. All right. Now then, so we've now got the fundamentals to create our laser. So how do we get about it? Right, let's have a look at a 2-level system then. So we've got a ground state and an excited state. That's all that means. So let's have a look initially at a ground state. So let me just draw here. There's my ground state. There's my excited state. All right, so I'll put over here excited. Sorry. And my ground state. Now, let's put all the electrons down here. This is going to be fun. All right, let's go 1, 2, 3, 4, 5, 6, 7, 8. Nice even number. Helps us with the maths. Right, photon comes in. Let's do a little photon here. Let's change the color of my pen. Photon comes in. Here it is. It's got exactly the right energy, E equals HF. So it's going to do its job. Now, the question you're going to ask yourself, all right, what's the probability of one of these electrons absorbing the exact amount of energy and being excited to the excited state? Well, statistically, all right, if we assume that it's going to interact with it, then one of them is going to go up. All right, so we got 100% probability of it happening. Great. Okay. So wait, we've got one up here now. Let's put another photon in at exactly the same frequency. Let's put photon number 2 in. So what's the probability now of exciting one of these or stimulating this one back down? Which one's more probable to happen? Well, if you said, well, it's more probable to excite another one, yeah, absolutely right. So let's excite another one. There it goes, up to there. So now we've got 2 excited, 6 not excited. Let's do the same thing. I think you can see where I'm going with this. All right, hang on, my pen's disappeared. There it is. So let's have 3, exactly the frequency. So now, is the probability going to be stimulated emission, i.e. getting one of these to fall back down to the ground state, or exciting one of these up to the excited state? Well, if you said excite, you're absolutely right. There we go. So we're now up to 3 in the excited state, and we've got 5 down there. Let's do one more. So what's the probability of exciting now? Is it more likely we're going to stimulate, i.e. cause one of these to fall back down, emitting 2 photons, or is it probability we're going to excite one of these? Well, if you said probability is going to excite, you're right. The probability isn't great, right? It's 5 out of 8, but there's still a statistical probability. So statistically, the chances are we're going to excite it up there. Right, let's put one more in. Let's put another photon of exactly the same frequency. Now, what's the probability of exciting now, or probability of stimulating? Well, I think you'll find at this point now, if you said it's about 50-50. Therefore, in a 2-level system, you're never, ever, ever going to get N2 greater than N1. In all probability, statistically, I mean, it may happen, but it's unlikely to happen with large numbers. Statistically, then it's going to be 50-50. So the next photon in, this 5th photon, is as equally as likely to stimulate as it is to excite. Therefore, a 2-level system will not work. All right? So a 2-level system will not work because of probability of exciting or getting a population inversion, i.e. more up in here and down here, is not probable. The most you're going to get in there statistically is 50%. Okay? So how do we do it then? We can't do it with a 2-level system. Well, obviously, we can do it because we have lasers. So let's try it with a 3-level system. Now, there's an applet there. If we get time at the end, I'll show it you. But if I don't get time to do it, just go onto that applet. It is a Java applet, which it runs in a separate window, so it will work. It's really nice to have a play around with that and just see how the 3-level system works, 2-level and 3-level system works, or for the case of 2-level, how it doesn't work. So let's have a look at a 3-level system then. All right. So I'm going to do my 3-level system. Where's my mouse gone? There it is. So let's do a 3-level system. I'm going to give myself some space here. So I'm going to do the ground state down here. I'm doing quite a long ground state. So I'm going to say ground state. I'm going to have an excited state all the way up the top here. I'm not going to have the excited state going all the way across. So this is just me making life easy for myself. And then I'm going to have this other state here. All right. So they're both excited states. I'm going to call this E equals 1. I'm going to call this E equals 2. All right, just for the simple explanation. And I got the ground state down there. Right. So where are all my electrons? Well, obviously, they're all down here. So let's draw a few in. That's enough. Now, what I want to do is I want to get these excited. I want them off this ground state, so I got a population inversion and I can stimulate them down. And the way I'm going to do that, I know a 2-level system doesn't work, so there's no point putting them to there. I'm going to excite them to there. And the way I do that is I'm going to pump in energy. All right. Now that energy could be through electron-electron collision. So I could just absolutely hammer them with electrons and give them energy, or I could use photons of light. Doesn't matter, all right, how you do it. All right, different systems use different ways. So I'm going to pump in energy. Now that energy I'm going to pump in, right, is equivalent to E equals HF. So I've lost my pen again. Where's it gone? There it is. All right, so I'm going to put in some a photon of light equals HF, right, and that is between ground state and E2. Right, so I'm going to pump them up from there straight up to here. All right. Now, in a way, we've got a 2-level system here. If I keep doing that, right? Eventually, after I got 50% of them up, I can't do any more. So what I want, even though it's up here, what I want is, as soon as it's up there, to increase my chances of stimulating up to here, or sorry, exciting up to here, not stimulating up to here, exciting up to here, I need this to be empty, all right? Because at this moment, I've got a 1 in, what was it, 2, 4, 6, 8 chance of getting it up, right? Now I've got a 7 and 8 chance of getting the next one up, which is not quite good enough. So I want this to be empty. So what I do is I make the lifetime of E2 about 1 times 10 to the minus 9 seconds, right? So that's a nanosecond. So a nanosecond after getting there, I want it to fall back down. But I don't want it to fall back down to there. I'm manipulating the system so it falls back down to there. Okay. Now this is empty. So the next one, 100% chance of getting it all the way up to there. All right. And again, as soon as it's there, it falls back down to here. And if I keep doing that, eventually I will have them all from here up to here and back down to here. So eventually I have them all down here now and nothing down there. So they've all gone. Now you're saying, oh, hang on a minute. Surely if they drop from here to there in a nanosecond, then they're going to drop from there back down to there in a nanosecond. And you're absolutely right. However, what we do is we manipulate the system so that E1 has a lifetime of about 1 times 10 to the minus 6 seconds. Now you're saying, oh, hang on, that is really, really short. But let's think this in electron terms. That level there, the length of time in that level there is 1,000 times longer than it is in that level there. And if you want to put that into perspective, just think if you were given an opportunity to live 1,000 times longer than your average lifespan. That is a very, very, very long time for an electron to stay here. An awful long time. Now, so hopefully we've got a population inversion. So that's what we want. So now we've got a population inversion. All we want is one of these, any one at all, to fall. So as it falls, you know what's going to happen. It's going to give off a photon in a random direction. Okay. Now that photon is going to stimulate another electron to fall. So there it goes. There you go. And now we've got 2 photons. And these, if you remember, are now coherent. They're in the same direction, the same phase, same frequency, same wavelength. They're coherent. Now those 2 will cause another 2 to fall down. And those 2 will emit 2 more photons of exactly the same energy and exactly the same direction. And what we've got is a build-up. So we've got here coherent light. And what we've got is 1 electron, or 1 photon, sorry, goes to 2, goes to 4, goes to 8, goes to 16, etc., etc. And you've got an exponential output, right, of light. All right. So in this system, a 3-level system, as long as you can manipulate your gases, right? In this case, we'd be using something like helium and neon because the energy levels can be interchanged, right? So as long as you've got these gases, then there we go. I've lost my pen again. I keep losing my pen. As long as we've got these lifetimes in here of about 10 times to the minus 9, and this one being about 1,000 times longer, we can get a population inversion. Once you've got this population inversion, we can then get stimulated emission. And all we want is one to be spontaneous, right? So that can be our spontaneous one, if you like. All right, and the rest to be stimulated. So we got 1 to 2 to 4 to 8 to 16, and we got an exponential increase in our output of light. So if a 3-level system works, then, oh, by the way, just to point out, right, you probably have realized it, but energy going in here, all right, is this much, all right? So that's the energy going in. Energy going out is that much, right? So you will need more energy going in and energy out. So where's the energy loss? Well, here you've got losses, and this is probably in infrared. So your lasers will get hot and need cooling. All right. So this is very, very inefficient. All right. You're probably looking about 1% efficiency, right, on the whole system. So the energy losses are massive. Okay, and you have to understand that as a laser. So that's a 3-level system, and a 3-level system works well. So why then, or what's the difference between a 3 and a 4-level system? Well, a 4-level system, let's go back to that color. Let's draw a 4-level system then. So again, we've got our ground state. This won't take long to explain because it's of the same principle. We've got our energy level up there we're going to pump to. We've got an energy level there, and we've got an energy level there. So we've got another energy level. So I'm going to go E equals 1, E equals 2, E equals 3, and this time E equals 4. So same thing, right? We got the electrons, there they are, electrons in the bottom, as we normally would, and let's pump them. E equals HF, right? So the right frequency to get them from there all the way up to there. So far, no difference at all, right? So they're going to be piling up here, and as soon as they pile up here, you don't want them here. So the lifetime of this is about 1 × 10 to -9 seconds again, right? They're going to fall down to here. And again, this is our metastable state, right? And it's going to be about 1 × 10 to -6 seconds. So that's what they call it. They call it the metastable state. All right. And they're going to fall up here, and they're going to collect here, right? Because the lifetime is again about 1,000 times longer. Now, you'll notice that E2 this time is empty. All right. So there's going to be, in this one, there is a chance that as this gives off a photon here, it might excite one of these to pop up to here because they're in this ground state. So there is a chance that as a photon is stimulated, or photons are stimulated, or one is spontaneous, could be absorbed by this photon and go up to there. So there is a chance it could go not up to there by this incoming energy, but by there by our output energy. So there is a chance because there's this ground state, it can have electrons in it waiting to be pumped back up. Okay, but if you notice in this one, E2 is going to be empty because in here we want the lifetime of this to be about 1 × 10 to -9 seconds again. So as they fall down, producing a photon, right, causing another one to fall down, giving me 2 photons. You can see where I'm going with this. Causing 2 to fall down, give me another 4 photons, right? And again, I've got my coherent light. Because as soon as they get there, they fall back down to E equals 0. This is always empty. There is very little chance, all right? So there's little chance of excitation. In other words, we've got a better laser, right? And when they've gone down to the bottom, we pump them back up to the top again, all right? So we've got this big circle. So this is better. So there is a greater population inversion between what have I labeled it as? I've labeled it as E2 and E3. Right, and if you've got a better population inversion, you've got a more powerful laser, right? So it makes it more powerful. You get more output. So that's the advantage. Now the disadvantage, if I get my red pen again, is you've got energy losses here. All right, so you've got energy losses here, probably as infrared. All right, so you've got energy loss. And also, you've probably worked out now, we've got energy loss here as well. All right, so you've got lots more energy loss. You need more energy going in because you're going to pump it from up to the fourth energy level here. If you take E1 as the ground state, so you've got more energy losses because you have to put more energy in for the same or more powerful light out, but there are more energy losses dropping for E4 to E3 and E2 to E1. Okay, so that is how we get a laser working. All right, so that is the theory behind it. Now, if I go back to here, so what is the process of pumping and its purpose? So pumping is putting energy into the system. So so the act of energy transfer to the gain medium, and the gain medium I'll talk about in a second. In other words, I'm putting energy in to excite those electrons, right? So this energy is absorbed. Right, by the medium, produce an excited state. So let me just squeeze that in there. That's all pumping is. So it's the act of putting in energy. Right. Now, what is the structure of a typical gas laser then? All right. So we do need to know this. So structure of a gas laser, what we need is a container. So we need a tube of some kind. All right. So if I just do I'll do it in 2D. It makes it probably a little bit easier. All right. So if I have a 2D cylinder, all right, and at one end I make it 100% reflective. So I'm just going to make this a mirror, and I'm going to put it 100% reflective. All right. And then inside here we've got my medium, so my amplifying medium. Oh, sorry. And that would be something like helium or neon, or helium neon. So that'd be a HENI laser. You might have heard of that. So that'll be in there. And then what I've got on this side, I'm going to just do a mirror. And this one will be probably about 90% reflective or 99% reflective. So what we do is we put energy into this gas here, and these electrons will do as they're told up here. They will excite and excite. Now, a lot of it won't go the way you want. So some of it will leave the sides. All right, if I change my color of my pen, all right, some of it will leave the sides like so and be lost forever. And it could be a couple of bits of coherent light going that way, or a few photons that are coherent going that way. But eventually, one photon will go exactly in that direction. Only need one, right? So it'll go that way, and then it'll bounce back. And it'll go and hit this mirror. Now, 99% of the time, it's going to bounce back again. So it's going to go back and forth along this axis. And every time it goes back and forth along this axis, it's going to stimulate another electron to fall down. So you will get losses. So if you've got lasers, there will be losses out the side, but we don't worry about them. They're small compared to the gains I'm going to get along this axis. And 1% of the light is transmitted. Okay, so only 1% of the light is transmitted in this direction. All right, and that's how it works. So we will get lots of losses as they go off in all random directions, but eventually we just need that one to go back and forth, and it'll go back about 100 times or 99 times, stimulating as it goes, and then 1% of that light goes out. So that's what the makeup of the mirror is. That's what it looks like right between two mirrors, and that's what's happening in between. So semiconductor lasers, the advantages, right, you notice they're very small, so we don't have to worry about that. They're small, they're cheap. All right, so lots of advantages of a laser, semiconductor laser. They're more efficient. When I say more efficient, we're not talking about hugely efficient. So these are about 40%. That's about 1%. So these are about 1% efficient because that's all the light that's coming out. All right, these are about 40%. So they're not massively efficient, but they're much more efficient than that. All right, and as you probably expect, easy to mass produce. And about 10 years ago, they were producing about 1 billion laser diodes annually. That's about 10 years ago. So they're probably doing much, much more than that now. because they're still used in many, many things. So where are they used? Just to finish off then, because I am out of time. So where are they used? They're used in CDs. They're used in barcode readers in your supermarkets. They're used in optical fibers. Yeah, infrared is in use optical. So lasers, use it in infrared lasers. Image scanning. And the last thing I'm going to do is laser surgery, as in laser eye surgery. So, or not even necessarily laser surgery. And there we go. Thank you very much for listening.
Thank you very much, Steve. And